Hi, what's up? So we're just gonna hop into this. This shouldn't take too long, and it's pretty simple. So first, we're gonna talk about what's in your average blood sample, right? So you're gonna have your not goblins. I always, I always think they're called goblins. Um, globulins, which is essentially used for like the immune system. You have your proteins, right? You have albumin, that's in your blood, a ton of it, right? It's used for important stuff we'll discuss later, but you have a ton of albumin in your blood. Your blood, your red blood cells, right? You have water in there too. You have platelets, and that's like your average run of the mill like blood sample, right? But protein wise, like you have a bunch of tiny amounts of proteins, but albumin is going to be number one, numero uno. And so, with that being discussed, we're going to talk about the average red blood cell too. So, your red blood cell is going to have 8 components, right? It's going to have 4 heme groups and 4 subglobulins. Oh my goodness, I cannot say that word to save my life, but we'll have 2 globulins, 2A and 2B, and they'll just work together to carry oxygen and nutrients to your body, right? And the thing is, these proteins, these heme groups, and the iron that's in them needs to be broken down once your blood cell has lived its relatively short life, right? Because they can only last 120 or so days until they're tired. They say, I'm tired, boss, and your immune system puts it down, right? It's a pretty quick process, and they tend to get cleaved and shut down in the liver, kidney, or spleen, right? Um, the materials can get transferred in different ways, all right? The iron gets transferred by, get this, transferrin. Thank you to the doctor that named it that instead of, like Dr. Sherlock or Hooper's theorem or whatever. Just made it transferrin, so thank you for that. So transferrin transfers the iron of decayed red blood cells into the red bone marrow, where it can be reused again for um, new red blood cells. And you have um, the heme groups. These heme groups, they're going to be a little more interesting. Some of them can just get recycled back, but a lot of it, if not most of it, will transfer with the albumin in the blood, right? Remember when I mentioned that less than 3 minutes ago? So this biliverdin, take out the iron, becomes bilirubin. It'll go down to the liver and it'll get some glucuronic acid slapped on the top of it, right? And then we got our upgraded bilirubin. It'll be go through bile and it'll also be found in bile, right? And it'll go through the bile duct into your intestines, in which it'll become a urobilinogen. And your urobilinogen can go in a few different places, right? It can just follow through, right? Go through your intestines and you'll poop it out. It's actually what gives that nice, tasty brown texture to your feces. So if you have like white poop, then there's probably something up with your liver and you should get that checked out. It can go to the kidneys and become urine, although I believe it's not urobilinogen, it becomes like urobilin, I believe, in the kidney. And then you just pee it out and, it gives it that nice, tasty yellow. And then it can also just go back to your bloodstream, where eventually it'll get cycled out just from the due process of time. But yeah, that's essentially what happens to your heme groups or your amino acids. It becomes biliverdin, then you subtract the iron, bilirubin. Bilirubin gets glucuronic acid in the liver, not kidneys, that'd be silly. Then it goes to the intestines, and there the bacteria, I didn't reiterate this enough, the bacteria eliminate the urobilinogen, or not the urobilinogen, the glucuronic acid, and that makes it urobilinogen. And then you can either poop it out, goes back in your blood, or it goes to the kidney and becomes urobilin. Whew, that's a mouthful and a half here. But we're making pretty good time right now, so I guess we'll just hop into this. So there's really 3 ways or so your body can reduce blood loss, right? It can coagulate and have a vascular spasm, or block. I'm forgetting the exact word usage here, but it can block using platelets. So we'll just cover that. Vascular spasm is exactly what it reads on the tin, right? Your blood vessels will constrict, it will reduce the amount of blood going there. And while effective for reducing blood flow, it by itself will not be enough to prevent all future blood loss. In your platelets, you'll have the VWF factor, or not platelets, I'm sorry, I'm tripping over my words. The VWF, which will go over to this, like, say, torn blood vessel or whatever. It will get to the collagen and it'll stick to it. The negative charge is very appealing to it. So it'll stick to it, and then platelets, which I've marked in purple, will stick to that, right? And so the platelets won't really stick to each other, but they will stick to that. And eventually you'll get like hundreds of thousands and millions of platelets, right, for the cut so you don't bleed out. And while they won't stick to each other, because it's stuck to this, and this is a mechanical receptor, as the blood flow pushes through it, it activates the platelets, which triggers its response here. So for example, you have your dense granule, the ADP and calcium, then you have your, I think it's oh my goodness, it's slipping my mind. Dense granules and alpha granules, not A granules, it's alpha granules. I would have been right in Greek though. But then the alpha granules will be activated. It'll summon PDGF, which is like this the healing factor. It'll help cause it to constrict and to reduce the size of that. Essentially, all of this works together to summon more platelets and to get more in that area so it can keep filling that hole. And so that's a blockage, essentially. You just want to stuff it as full as possible. And then you have I think it's coagulation. I'm mixing it up now. Yeah, coagulation here. The cascade. So this is how we get that. If you've seen those pictures of the platelets and blood cells getting covered, clotting. This is clotting. This is blockage or coagulation, vascular spasm. Okay. So the main job of this is to get fibrin on the scene, and so it can create this clot around the area. And so there's two branches of it. You have intrinsic and extrinsic. We'll start with intrinsic, right? So you have the Hageman factor, 12. 12 becomes 12A. 11 becomes 11A. I'm not making this up. This is what I was told, right? This is what I know. And then you have 11A. 11A becomes just 7 because it can. And then 10 hits off 7. And then 10 becomes 10A plus 5. And then 2, the prothrombin, hits off the 10A. Man, if it was a TV, it'd have a really good signal because it has a 10A. I just thought of that off the cuff. It had to be said. All right, we're just going to keep moving on. And then the prothrombin, or the 2, hits off the 10A. And then the 2A, which is the thrombin itself, big deal, is what enables the fibrinogen, which is in your bloodstream, right, but unactivated, because that fibrinogen, if activated, can form 1A fibrin. And fibrin forms those nets that create really good clots that are great for, preventing blood loss, but also really good at killing you. Because think, you just have this embolism flowing around, or is it here? You have this clot just flowing around in your body, right? Goes through your foot, it's fine. It goes up your leg, through your chest. Maybe it gets stuck in a carotid artery. Who knows? It goes all the way up into your brain. You have a clot in your brain, you're dead, right? You can see the issue with this, and we'll talk about later on how your body deals with this. But just know that thrombin 2A is what activates fibrinogen into fibrin. And then we have an extrinsic factor, which is when it's injured outside, right? And that's 7A becomes 7A, and then 10 becomes 10A. And remember, 10A, 10 plus 5, the prothrombin is activated by 10A, and then the thrombin is knocked off the fibrinogen and becomes 1A fibrin. Yeah. notice how this part is common here. Right? It's shared by both the intrinsic and extrinsic. Because regardless of what happens, it still needs that prothrombin to become thrombin to get the fibrinogen into fibrin. And so you're probably thinking, Nick, wow, that was super good and super well explained. You're welcome. Well, I'm joking. I can always do better. But essentially, it's like, how does this like not happen all of the time? Like, what is your body's counterplay? Because prothrombin, it activates a bunch of other stuff too, right? It's a positive feedback loop, and whenever you hear positive feedback loop in biology, you should have a heart attack, because 99.9% of the time you're screwed if you have a positive feedback loop. No one will never fear. PTA is here. So your regular endothelial cells and like blood vessels, for example, right, they'll produce PTA. And PTA activates plasminogen. And you're probably thinking, what's plasminogen? And I'll say just another protein in the street. It's really not important, except for the fact it can activate plasminogen to become plasmin, I think it is, right? I'm like 95% sure it's plasmin. It's something of the plasma sort. I know that for a fact. Yeah, I think it's plasmin. But plasmin, what it does is it tears down fibrin, right? Which is really good. So it'll sort of auto-create this area where, yeah, there's a bunch of fibrin being produced and holding it down because these cells are struggling to survive, right? And they're not really producing that much PTA because, the endothelial cells were torn off. But everywhere outside of it is near healthy as can be, right? And so they're going to be producing that PTA, which will activate the plasminogen to become plasmin to reduce any potential clots, which is really important. And so imagine a situation, this was just shared with me in class, and I actually really enjoyed it. You have your sepsis, right? You have a cut, bacteria gets in there, and it gets like your arm sick, right? Or that region surrounding it at least, right? And so that region is sick. What's going to happen to PTA production in that arm? It's going to drop, right? Because it's sick. These cells aren't healthy. They can't make it. And what's that going to do to the number of clots forming? It's going to increase it. So you can see that issue there. I think that's super neat. Well, obviously that's an atrocious thing, and you really don't want that to happen to anyone, but it's really interesting because you really see how badly this can hit the fan, because if that arm stays infected, you're going to get clots coming up, your venous return, and that's going to get caught maybe in the small arterioles of the heart or maybe in the blood-brain barrier, but it's going to screw you somehow, some way, and so you got to fix it fast. And so you can do different tests, right, to see what's working, what's not, right? So you have PT for this. It's really good at detecting level of vitamin K, which is important. Or is it B? Vitamin K, I think, for detecting stuff like this. Then you have PTT, which I remember because it looks like the 2 1s and the 12 in Roman numerals holding each other. And their respective jobs is to test how effective those things are working out. So if they're super high, maybe that's a good sign that something's wrong with you. But that's just what I've learned with this so far. I really enjoyed this. The numbers can be tricky. But yeah, that's what I've learned, and thank you for watching.